Thank you. It's a pleasure to be here and join this discussion of nanorobotics and for uses for medicine. I hope to learn a lot from you over the next day or so of other kinds of applications that we might look at for nanorobotics. What I'm going to be describing today is one particular problem, and that is how might we power tiny robots operating inside capillaries. I don't think I need to go over much of the motivation. We've heard about that a bit already in the talks earlier today. But let me just mention a number of issues that come up in how we might get to make these robots and have them useful for us for medicine as opposed to just being conceptual nice ideas. There's questions of how we might fabricate them, how do we control them, how do we power them, identify particular applications for which they will be suitable and able to do things that we're not able at all to do with current medical technologies. I'm focusing today on just the issue of power. And in the context of power, there's really two classes of problems. One, you can think of applications in which the time in which the robot's going to operate is relatively short, and you could put some kind of fuel inside the robot, and that's going to be sufficient for for its task. And the other possibility is for more extended operation, and that's what I'll be focusing on today, in particular looking at chemical fuels that the robots can get from their environment. The particular source of power that I'm going to look at today is oxidizing glucose. This is a particularly appealing method for operation inside the bloodstream because glucose is around and easily available, as well as oxygen. So we're basically going to be talking about having some kind of fuel cells that are similar to what is in some kind of some bacteria that are able to oxidize glucose. And the idea of this study is just to get some kind of quantitative estimates of how much power robots operating in capillaries will have available to them through this method and what sorts of capabilities that amount of power will deliver. So that's going to be the first question. How much power can you expect to have? And of course, the secondary question when you're thinking about medical applications is, would that be safe? Are there some kind of issues that the power generation of the robots would cause for the surrounding tissue or the body? So I'm going to have a look a bit at both of these questions. And the method I'm going to be using is, this is basically a preliminary quantitative engineering design study. And the idea then is to pick a medical application context, in a fairly generic one that will likely come up in many different scenarios. If you have other ideas, I'd be more than happy to discuss them and hear about them later. In this particular application, try to identify what are the key constraints on the amount of power available, and then evaluate how much power is available and what might the implications be for the body. So the application I'm going to be looking at basically is robots operating in the bloodstream. So this would be basically for a task where you're having the robot, say, look around for cancer cells or other diagnostic purposes or deliver drugs, and so that they're just patrolling the body for some particular medical either treatment or diagnostics, with the ability for these devices to pass near cells throughout the body, and that can give them a great capability of, say, in particular, say, looking for a small number of cancer cells that might just be starting well before it would be noticed on any kind of much larger scale imaging or diagnosis. I'm going to be focusing, again, just as a specific example of self-assembled groups of these devices on just sitting on a vessel wall, monitoring for interesting chemical signatures or various passing devices, or perhaps just doing some kind of computation. Now, when we come to glucose and oxygen, the key question is, okay, what's the limiting factor, or the limiting chemical? And if we just look at the chemical reaction for combining glucose and oxygen and the concentrations that are available, we realize basically oxygen is the rate-limiting chemical. And so that's what I'm going to be focusing on. What is the availability of oxygen? Glucose concentrations typically are much, much higher and will not be the limiting factor. So we realize that most oxygen, of course, is carried in red cells bound to hemoglobin with much higher concentrations than is available in plasma. And so one of the key issues is how does that oxygen come out, and how is that affected by the potential of robots that might be drawing the oxygen and consuming it much more rapidly than the surrounding tissue. So in terms of modeling, we need to look at how does chemical transport get the oxygen from the red cells to the blood, to the plasma, to these devices, and then what is the consequences for power and on the surrounding tissue. There's a number of both modeling challenges as we think of putting together a quantitative model for these devices. And first is complex geometry, the behavior of the cells, and in particular the kinetics of oxygen release from cells. So I'm going to just give you a simplified version of the geometry, just axial symmetric vessels. And this is actually a fairly old model of looking at oxygen transport in microvessels, going back almost 100 years. And so basically you have some tissue surrounding capillaries, and we look then at the behavior within one of these capillaries and the surrounding tissue. And here's basically the idea of having a group of robots that are sitting on the inside wall of a capillary, not big enough to block the vessel, so that the idea is that these are tiny machines that can travel through capillaries. So we're thinking about micron-sized devices, and then they can self-assemble on a capillary wall for some purpose, say, of monitoring or doing some computation. A particular challenge for a model of this behavior is the fact that cells, as they're passing by, are not just static spheres or so. They actually distort in order to go through the capillaries. The cells in their sort of resting configuration are somewhat bigger than the capillaries and distort to go through. And we basically are going to model this following what a number of people have looked at in terms of mechanical studies of how cells go through and distort, to basically see how it is that the cells move by the group of robots that are on the vessel wall. And this is showing you a cross-section. The second issue is to deal with the kinetics of oxygen release from the cells. We might also, in a very simple way, think of red blood cells as like trucks that take oxygen from the lungs to the tissue, but because it's diffusion at the end in the release, the concentration always has to be higher in the cells and the plasma than it is in the tissue. And a consequence of that is that the red blood cells actually take with them a lot of the oxygen they bring in, they can't release because their concentration has to be always higher than it will be in the tissue. So they're not as effective at releasing oxygen as you might think a little truck would be. And this is actually one of the other areas that the respirocytes have an advantage, because they have active pumps and they can put oxygen out and take carbon dioxide in much more effectively than red blood cells, as well as being able to store more of it. So one of the issues is that the robots can have much higher power densities, as we'll see, than is common in tissue. And so they can create much larger gradients in the oxygen concentration than is typical in body tissue. And this raises the question that cells that are carrying a lot of the oxygen, they may pass the robots before they have a chance to release the oxygen. And so kinetics is an important aspect of modeling this behavior. Fortunately, people have looked at this issue, and for the numerical model I'm going to be showing you, we can just go back and make use of some numerical models of how oxygen is released from blood cells as a function of the concentration in the surrounding blood. So the numerical model I'm going to then just be describing takes into account low Reynolds number fluid flow in the small vessels, oxygen transport from the cells, diffusion in the plasma and tissue, and then looks at power generation both in the robots and the surrounding tissue. Now let me then turn to results from this numerical model. And again, the motivation here is to give us an idea of what the kind of capabilities we would expect these machines to have in terms of power, what that enables, and then what might be some of the consequences on the surrounding tissue.